Record. So okay, let's continue with what we ended last time. So we I'm a little bit quick review. Like basically, we are trying to explain SIFT or like actually mainly SIFT, like a local feature extractor method. So it's a the main motivation is if we have like two images, if we're trying to match one image from another, so we want to kind of extract some local features more precisely. Like I want to from an image, like find some distinct points there, like known as the key point. Then once we determine the key points, then like we are going to like create a descriptor. So last time we said that okay, if we create this two, okay, fine for detection, like if you remember, like we can either use okay corner Harris corner detector will be the most basic, but it won't be scale invariant. So we say that like okay, maybe we can look for different scales, and eventually for SIFT, like it chose to use a difference of Gaussian. So basically, like, for different scale, it do a different Gaussian burring, and then they across different level, they take the difference, and then so you have a three-dimensional structure. So maybe I shift back to um, like this one, right? Then we just like find the maximum across like both the scale dimension, also the pixel dimension, XY dimension. So for that will be the maximum there will be basically the descriptor. So, and sorry, not the descriptor, what will be the key point. So, and for the descriptor, um, for that location, so last time we said that like for C for like many similar methods, basically use a histogram of oriented gradient. So basically like this, if we have the point that we're interested in is here, then we are going to across the neighborhood for this for okay for this labeling like 4 by 4 patches. So I have like so therefore in total is 16 by 16 windows. For each of them, like we trying to compute the histogram in each of this window here. Um, s- sorry, not window. Each of this patch here, each of this block here, 4 by 4 block here, and so and then I hope that's not okay. I guess it's probably one of these. Okay, this Discord message. Okay, so and and then like so because we have like this is a little bit distracting. So so with this uh which each of this block here will have a distinctive histogram. So will be like the histogram have 8 bins there, uh and so therefore like we have like 8 numbers. So in total there will be like 128 as we mentioned last time. um and so okay, I guess I'm to make sure that it's like or kind of like rotational invariance. So a trick is that we can shift the histogram to make sure that like overall we'll always start with the histogram with the largest value. Sorry, or like yeah, the peak of the histogram will shift to the beginning. So okay, so that's the main idea, and then we there's some alternative like of SIF, like a pretty famous one is known as Surf, and it's also like in OpenCV, but like I tried that like uh you cannot use that like right away because I guess the it's still like the patent is not expired. I'm not sure about SIF. Like both of them, to use that you are supposed to install the OpenCV. Let's see. Let me open. Okay, I guess I can just use this getting started one. Yeah. So what I mean is like, like we pip install that OpenCV Python, right? So that's so if you want to use SIFT, you should install the long feed package that is this one. Oh, okay. Probably like OpenCV Python. Yeah. So but I just tried yesterday. Like it used to be like for I have the most latest version, right? Let's see. My 3.2 4.5.1. SIFT is available, but Surf is not. At least if I install just like this, I use a pip install. Like it's not. I cannot run Surf right away. Uh, I already put up another homework for that. Another homework you need to use SIFT, so you need to make sure you install this like OpenCV contribute Python uh, package as well. And for SIFT, it should work fine. And for earlier version, I think you can even use Surf. Yeah. Somehow, I last year I remember if I use a version 3 point something, I can use Surf as well. So anyway, um, besides SIFT and Surf, like yeah, I will just skip it. I guess I don't have too much time today. I will see like if how time. Okay, I would like to talk about this one though. Like LBP is another like rather popular descriptor. Uh, so the idea is pretty simple. So as you see here, what it did is like if I want to describe uh, a pixel and the value in this, like let's say at this location here, I'll basically compare this value like with its neighborhood. So if it's like its neighborhood is bigger than itself, then I would say one, otherwise it would be zero. So as you see here, I have 1, 2, 7, 3, 8, 2, 3, 5 here. So then I will have like 0, 0, 1, 0, something like this, right? Now, then let's say I start from the upper left corner. I just say this is one and so on. I count onward. So so they would so basically I consider this is like 8-bit numbers. Starting this is the least significant bit until this is the most significant bit, right? So therefore, like for the most significant bit here, will contribute a value 128 and so on and so forth. Then I convert this into a this number, like basically, then will be just equal to in this case will be, oops, I guess somehow this, wow, that's very weird. Okay, will be like 128 plus 16 plus 2, right? So therefore I got 146. So is that clear? So I guess I here maybe it's a good pause to make sure you guys know what I talk about. So let's say give another example. So if see if you guys can do that. So let's say now again, this is the least significant bit, and this is the most significant bit here. So I go like this direction from least to most. So let's say if I have this is a 100, and this is 99, and 5, 101, and 125, 140, 0, and 0, 10, 10, say. So what was the LBP descriptor for this one? LBP or LPP? I forgot. Question here. So you guys are trying to work on that, or like you just got lost? Okay, that's good. So someone try to. On the left is a 99, 10, and 10. So maybe I try to copy that and make it zoom in or somehow. Okay, let's see. Yeah, that is better. Maybe. It's like, but how you shouldn't get a number larger than 256 because it's an 8-bit number, right? You have 8-bit here, like from this significant bit to the most significant bit here, right? Somehow, if you're bigger than 250, 255, then something is like not quite right, honestly. So yeah, I don't know. I didn't. Yeah, I don't know. I just wondering give this number here. So I need to count them as well. Uh, so but you guys are still trying. Like okay, let me go back to that example, then come back to here. So how it works is like this, right? So you have just like you want to find the local, have a local descriptor for this patch here. So it's a very kind of small 3 by 3 block here. So what it did is say, okay, I will compare the neighborhood with like the central pixel here. So the central pixel here, let's say is a value 4 here. And so therefore, like I would just look at whether it's bigger or smaller. So if bigger, I will count as 1. If it's smaller, it's 0, right? So therefore, I have 0, 1, 0, 0, 1, 0, 1, something like that, right? Then I would just think of this thing as a number. So starting from this one as this upper left is like the least significant bit and move on up to the most significant bit, right? So then if I think of this as a binary number, from least to most significant bit, then will be just equal to uh, okay, if you think of this as a number, how do you convert like binary numbers to like to a decimal? So it'll be just like if I have 1 there, that okay, then will be just okay, maybe like I should just say that. So if I seal here, this one I don't care, right? If I have 1, what's this bit correspond to? Like it's correspond to value 2 here, right? Because like the first this significant bit is have correspond to value 1, the next bit correspond to value 2, and the next bit correspond to value 4 and 8 and so on, right? So I'm 0, I don't care, right? This is should be 4, but it's 0, then I don't care. This is 8, I don't care. This is 16, so I need to add this 16, right? So therefore I have 2 plus 16, and then this 0, 0 here, 2 plus 16 plus 128, right? So therefore like it will be 146. So now get back to this. Yes, I'm sorry. Like, so I yeah. So I now can you work on this one again? Okay, okay. Again. It shouldn't be 491 because it's a oh wait. Yeah, it's a 8-bit a bit 8-bit number, right? Because there's a value here, right? So if you know like any 8-bit number will be less than 255 because if I got all of them, one will be exactly 255. So because this is 1, 2, 4, 8, 16, 32, 64, 128, and you add all this together will be 255, right? Uh, so anything larger than 255 cannot be correct, right? Because Okay, most likely the one give this So anyone are still working on that? Yeah. So I get more answer. I guess I just move on here. So let's see, right? So this say this is a like significant, right? Zero zero. So this is one. Maybe I just start counting anyway. So this is zero zero, and then I one two. This is four, right? And then this is A. This 16, right? This is a zero again. I don't care. This zero zero, right? So then 4 plus 8 plus 16. So yeah, it's 28. Yes. So okay. Let's move on. Um, let me pull your chat down as well. Um, so this is just an illustration of the LBP. I'm actually with this LBP uh kind of like descriptor. You can see that like you can argue that like you can based on the descriptor to determine different kind of uh low level like I mean like low level texture like or like low level feature of that at that point, whether it's actually just a spot or like it's an edge or like a corner and so on. So and uh and by the way, the LBP I just described is not rotational invariant, but we can easily create a rotational invariant one that described as rotational invariant. So basically what we do here, like in this example, again, like I have this original patch like this, or like here, it compare with this like A neighborhood, right? And now if I rotate it, you see like I rotate it, then like this 55 rotated to here, right? And this 52 here, like original at this here. Sorry, I should go like this. I have 55 rotated to here, right? So you can say it's rotated by 90 degrees, say counterclockwise, and this 52 here, 52 here, rotate to here, like again, like 90 degrees counterclockwise. So if I only consider LBP, then let's say I start with this time. Okay, it's a this time we use a different uh starting point as like this if it can be. Let's say start from here and rotate this way. So then like the LBP for the original one will be like have a number 1011, right? And it turns out to be what the value is 11. And if after the rotation here for this one here, I will have this one here. Let's see, this is a 110 up to 10, right? So because this is the least if it can be like I move here, so apparently it will be different, right? So I have the representation is not rotational invariant. Now I want to make it rotational invariant. So what we're going to do here is that let's see. Okay, yeah. So what we're going to do is across this A label here, I will just this one is the maximum, right? I know this one is maximum. So then what I'm going to do is I'm always have just take the maximum, start from the maximum as the least significant bit. So therefore, like I have this yellow pixel here, uh, it will be the least significant bit, and then I just count uh onward like this, yeah, in a clockwise direction. So then the number will be, so if okay, actually more natural, like I start from this. So this is a least significant bit. I can clockwise uh will be like from least significant bit to most significant bit, or I can start from here, like right, the most significant bit and counterclockwise. So therefore I will have like 0, 1, 1, 0, 0, 0, 0, 1 here, right? So now even after rotation, I still have this 2 to 1 here will be the least significant bit. So therefore the number is still like 0, 1, 1 and so on. Yeah. So this make the rotational invariant. And let's see. Oops, where am I? So okay, then we have like some we have described some how to have find keep-on and descriptor. Now finally, if I want to do matching, we need to like determine uh, how we say something is similar, not similar. So so this is just give the example again. So I want to eventually want to have this trying to able to match with like the correct one, this one instead of like this one, say, or like it's this one, this one, this one. And of course I have the descriptor. If the descriptor is a relatively similar, maybe like we can like say just use the Euclidean distance to kind of like compare them. Um, Actually, a better way like is often use the cosine distance instead. So, you can do the cosine similarity will be just uh, compute the dot product basically, and in that case, like the value like if it's bigger then it's more similar. So you want to look for the one is like have a bigger value. So so that uh okay, okay. One thing then the final thing I guess we need to worry about is like so let's say no matter you're using Euclidean distance or like cosine similarity. So if let's say if I have this maybe this one here, right? This one I trying to find a match in out of these two here. The problem is that I don't have a match, right? So if I just look for the most similar one, I will get into this one, right? If I look for, let's say, compare with the Yuki distance, again, the closest distance will be this guy, right? Or like cosine similarity, the closest one with this one. But this is not exactly a match, right? Compare this one here with this one is not exactly a match. So therefore, we want to also make sure that like we able to distinct actual match or just something similar. So uh, one way to do that is also like the simplest way will be, okay, let's compare the ratio of the best match and the next best match. So I have the, if you think of like, let's say, if I have, say, let's say I have like this image here trying to match with something else here, let's say, okay, this is different here. And I have two cases here, let's say. So let's say here I have some real match here. This one match with this guy here, right? And this one doesn't have a real match, and then these two match with these two, let's say. Now for the one with the real match here, we expect the similarity for this guy here probably is quite a bit larger than the similarity for the next best match. On the other hand, if like this one, these two like doesn't have a real match here, most likely both of them are quite close, but maybe one is a tiny bit better than like higher than the other. So therefore, one way to uh, determine whether it's a real match or not is simply compare like the ratio between the best match and the next best match. So then like if the ratio is like is is uh it's kind of like it's close to one, then we'll say like the matches are too close, then like you say okay, it's most likely it's not really a match. So if it's like tends to zero, then it's good. So therefore, typically what people do is I just get a threshold and then I compare that. Um and uh, and so here I will skip this one also. So okay, this is just a quick summary for this one. Okay, keep on descriptor, keep on detection, like determine keep on. So we describe like Again, Harris corner detector will be the simplest one, and we can apply other approaches like SIFT is the most popular one to determine key point. And also SIFT also available like after it's two things like after you determine the key points, also find the descriptor. So we kind of like mentioned that most descriptor is actually based on this histogram of oriented gradient, um, and the variation of that. So that's a quick summary. Okay, before I move on, like one thing is very important that I don't want to forget. So is that like we need to talk about the presentation next week. Um, I hope the presenters. I'm looking for. So for some reason, my computer is very slow. I don't know why. Let's see. Oh, its VirtualBox is running quite heavy. I guess I can kill this com thing here, probably. Okay, anyway. So so what I want to say is that a little bit about the logistic. So I hope that Heidi and Sarah is here. Is that are you guys are here? Heidi is here. I think like Sarah is that here. Yeah, Sarah is here as well. So uh, you you guys, I know that you guys are team up like to discuss to present the same topic. So I guess like that probably is better like to you guys to move in the same day. So then I maybe give a consecutive talk that would be more efficient. So Sarah, can you move up to here? Let's say maybe uh moved up to like March 16. Then I guess I uh is Uma here? Let's see. Yeah, Uma is here as well. So Uma, can you move down to like 18? So are you guys uh
That is fine with me.
yeah,
Yeah,
so Sarah is okay. Okay, that's good. So then okay, what we have, okay, I will change the date then. I saw Sarah, you're going to move up. I will change that right afterward the class. And and then I guess maybe better to have more to give the his first presentation. Then afterward, then Heidi and Sarah, you can just have all your time basically. So uh, actually, I had a meeting, a short meeting during the presentation. I may need to step out for 30 minutes or something. But it's yeah, I have the TA in case I have any issue. So okay, so that's the plan then. So that's the thing. I'm also like know that for you guys are the presenters, please really well prepared. Like because at this time, like we trying to pack like 3 presentations like per day per class. Uh, it will be really the schedule will be really tight. So then you really control your time really well. So I asked the TA that like we'll cut off the mic like precisely 25 minutes. You don't want to like overtime. So we just have to move on. Like so you have exact kind of like not more than you can have a little bit less. So I preferably try to finish not try to finish, but like control your presentation 20 to 25 minutes. But like way over 25 minutes, we probably need to cut off the mic. So If if you haven't presented for a while, you probably want to like do a dry one or something like that, because especially for native speaker, like you just thinking, okay, it's my own language, how can I cannot control the time or something. But like from my experience, I actually native speakers more likely to be overtime, because I uh, typical native speakers are more confident. They probably won't do a dry one, so they just okay prepare the presentation and then just talk about that. They can easily run overtime a lot. So okay, that's just my remark here. So okay, so that's we will move on. Um, so appends in my virtual boxes, I let me just save this and then close one of the presentation. I don't know why the virtual box list seems to be running lots of resources. So immediate next thing I'd like to talk about is like alignment. So yes, I will update the schedule right after the class. So um and so the so it's very natural, right? So now we have the keep on, we have the descriptor, we know the matches. So then we can do something like kind of stitching images. So basically that will be your homework fee, is trying to implement some function to stitch images. So just a quick review again, like with image warping, like remember that like because for translation, we want to put all this image transform, affine transform into a matrix multiplication. And it cannot be done without uh, kind of introducing this homogeneous coordinate. So if we just use the Euclidean coordinate, translation won't be a matrix multiplication. So therefore, like we said that we have this homogeneous coordinate, simply like padding this dummy coordinate here. And in reality, like if we have this is non, it's not one here, so we will just normalize that as the actual coordinate. Right? So the real coordinate, like in this case, just x over w, y over w. And so and this is example again that you see that like saw that like a couple classes before. So translation is like this. We have scaling, like rotation, shearing, and so on, right? Um, and also like we have the homography. By the way, like do you guys remember maybe a question like uh, for affine transform, what's the last row here? What's the value of this last row here for affine transform? So this one is a homography. Homography like will be like all the yes. Okay, good. Yeah. So and so homography like affine transform will be like everything like if the original is parallel, it's also be parallel, but affine transform be it's most general uh in terms of like matrix multiplication. So you can have um something like that, right? This is this square here that can be like totally mapped into something like this. So this is another example. And so okay, here the basically like from what we discussed earlier, we are able to find this matching point, right? We have like some key points, and we determine we have the descriptors, and then we determine the match. Maybe this can be the matches here. So you see, like for example, like this match pretty well, like this G match, this is G here, something like, and I have this S, some points with this S, kind of more or less match to here. This is like some realistic result, like you will have matching like this. But you also have outliers, right? So this point I totally match to something not relevant, not related. And also like this um let's see, yeah, so you apparently some good matches, some bad matches. um and Now given these matches here, how can I if I want to warp this comic book, it's not a comic book but this book match to this one here, So basically, I want to rotate or or like rotate and like scale this one into this one here. So how I'm able to do that? So then like basically this scaling and rotation will end up combine into this homography, right? So then the thing is I just want to determine this homography matrix. So if I can find this homography matrix, then I can just apply this on this image here and can warp into this guy here, right? So this is one example like we illustrated in the past, right? So for example, if I want to do image stitching, I have this image, I will just find the homography that to kind of uh, kind of project this image into this one here, and then project this image into this one here, and then I can stitch them together. So this is another example, like simple case that's like two image only involve a translation. So now I have, so these two images actually just shifted. So that's even no rotation and scaling. So only translation, I have this is okay, the first image, the second image, then you see like if my uh, second image if it's translated like this, then it's already like very much uh, actually not complete. Yeah, actually very nicely like able to stitch them together. Uh, in this case, it will be easy to find this translation because I say if I have the matching points here, it's like this, right? So the the translation in this case I can just take, let's say if I have this point match with this point, this point match with this point, this point match with this point, and so on, right? Then the translation, like let's say if I only take this point and approximate the translation will be just the difference, right? So will be just, let's say uh for example, if I take the I match there, will be just xi pi minus xi and yi pi minus yi. Right? So then if I want to take advantage of them, then I can just simply take the average. So then in this case, actually pretty simple. So I can find this uh, translation matrix. So uh, okay, what is the translation matrix? Like, do you remember? Okay, that would be like uh, com- 8 numbers. If it's translation xt and yt, what's the translation matrix? You saw that in the slides a couple. I mean, uh, couple of slides before, but like, do you still remember that? Actually, it's good to be able to remember what's the translation matrix. Something like, uh, you shouldn't need to go for a book to find that. Yes, it's uh, okay. Make sure you're writing a matrix, not a vector, though. Yeah. So no one remember that. Okay, that's fine. I'm not going to give the answer. So you okay. So but anyway, let's go ahead. Um, but I have, so this is an affine transform. Um so for affine transform, also let's say like if I want to uh kind of uh kind of like here, like as I said, like this here I only restricted to like translation, right? So let's say if I am going uh to be more general, so let's say I will allow this projection to be a fine transform. Then as you guys just mentioned that like the last word here is 0, 0, 1. So in this case, I have 6 variables, right? I have 6 variables. Am I supposed to uh okay, how many matches do I need? Uh so I have 6 variables here. So if I want to find these 6 variables, at least how many variables do I need to solve these 6 parameters here? So many of you still typing the, yeah, okay. Mm, the question is like, let's say you see, right, if I want to, uh, I want to find the affine transform here, that's basically determine this matrix here. So this matrix has 6 variables here, right? Now, how many matches is like meaning that like one point here match to another point here in another image. How many matches do I need to kind of solve these 6 variables here? So okay, you guys need to think a little bit like that's 6 variables, but each match, how many equation do you have? Definitely you have one equation, but are you sure you only have one equation, or maybe you have more than one equations? So let's see. Actually, uh, we have like how many unknowns? Like we already said the 6 unknowns here, right? Uh, but like for per match, how many equation do we have? Like, so let's see. So if this basically like I x pi y pi and 1, and I have x y 1, right? For each match, I have like I have like a pair of x pi y pi and x y, right? So I basically can write in this like matrix equation here, or like I can just have like expand that like into this way. So I have ax plus by plus c is equal to x pi, and dx plus ey plus f is equal to y pi here, right? So actually for each match you have 2 equations, right? Because you have one equation, ax plus by plus c is equal to x pi. Note that like here like you need to be um careful, like I mean not just I mean to have your mind clear in the sense that what are the variable and what are the unknown. X, Y here are not the variables. Oftentimes we look at some equation, we always assume that X, Y and those things are variables. But in this case, X, Y are not the variables, right? A, B, C, D, F here are the variables. So I have like A, B, C here variables, and I given X, Y, and X pi, Y pi, right? These are not unknown here. And for each, again, for each pair of xy and x pi, y pi, I have one equation x pi equal to ax plus by plus c here, and another equation y pi is equal to dx plus cy plus f here. So therefore, like each equation, sorry, each match, you have 2 equations, and you have 6 unknowns here, so you need just 3 equations, right? So, and but you can use more than 3. So you was trying to solve a over constraint, or like over, yeah, linear kind of linear equation like this, but you have like more equation than unknown here. And so then you can say this is a, this is x is equal to b, something like ax times b here. And if you have n matches here, a would be like 2n times, oh wait a second, why 6, yeah, 6, yeah, 2m times 6, yeah, size the dimension of 2m times 6, right? And so how to solve this? I guess we talked about that before, probably. Um, or maybe I talk about it in other class. So, but I guess I won't go into this like details. So this is like just solving like ax minus b. So trying to minimize, sorry, at minus b here. Trying to minimize at minus b, and uh, the second law of at minus b, the norm of at minus b. And did I talk about that before, really? Uh, in this class? Uh, yeah, but anyway, like, okay, but okay, I think like you, if you Okay, this is a participation question. Did I talk about something like that before in this class? I forget. Like solving AT minus solving like or solving this. Okay, okay. So okay, I just high level talk about that, like because I don't want to spend too much time on equations. So like this, so you can think of this as just and apparently this is a optimization problem, right? It's an unconstrained optimization problem. So you can just solve it like uh finding the gradient. So this is like just okay, this is just a scalar function, right? So at minus b, I'm norm of that. This is just a scalar value, right? So if I take the gradient with respect to t here, so I can expand this. I can think of this as a function of t here, right? So I expand that 18 minus something like that, right? So this second norm is just equal to uh, so this is a column vector, this is a row vector. So this is a row vector multiplied by a column vector. So therefore it's a just a scalar value, right? So then I can expand, that would be something like that, right? Expand to several values. Now what you see is I actually have like t other variables, right? I have t multiplied by some matrix multiplied by t here, and t multiplied by something like this, and this one multiplied by t here. Notice these two values actually are the same because I have like A is actually symmetric here. Wait, uh, is asymmetric? No, sorry about that. A is not symmetric. Okay, okay, okay. They are not the same. A is not symmetric. So, but anyway, like they have similar form. I have like T transpose multiplied by this. This is a row vector. This is a column vector, and B transpose A here is a row vector. T is a column vector, and 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 you can okay, this is not rigorous, but I guess you can think of this as similar to in for a scalar function here, not a vector function, a scalar function. You have um, let me move to here. So I have this ft again is something like a t minus b, right, square. When we expand that, it's something like t transpose a. Let's see. I guess I rather really expand a t minus b transpose a t minus b. So then, yeah, this will be t transpose a t minus b transpose a t minus uh, t transpose a transpose b. And that's one more term I don't care because it's actually, let me write anyway. So I'm also plus b transpose b here. Uh, so I want to take the gradient of f with respect to t here, right? So with respect to t, this is just 0 here. I don't care. And the rest is, you see, is like some form here. This is like something like t transpose ct, right? This I can figure out a transpose a is a major t transpose ct. And this is something like maybe d t, right? Something like d transpose t. Or maybe I can write t transpose d as well. So these two will be just the same. And if I, let's say, actually, like if you think of like what is the, if you take an analogy, okay, if I consider scalar, so I don't know why so many call today. So this one, if I cut degenerate into the scalar case, now t is vector here, right? But if I degenerate to scalar case, would be like, let's say, at something 80. So the derivative of at with respect to t will be just a, right? So here I'm not going to derive that, but you will expect this. If I degenerate from the vector case to scalar case, I will get something like it's also like a. So actually the derivative of like d transpose t, or like the gradient with respect to d should be just equal to d. Note that d dove here is a vector, right? So, but of course, if it kind of like degenerate to the scalar case, oh, this is something that you want to verify sometimes. Like after you do computation, let's say I get something, this value is like, let's say you get something like d square, I don't know why you get something like that. Then you immediately know that you are not right? Because if you consider the degenerate case, okay, let's say if I consider these are both scalar, then I should get A, right? I should get, or like, let's say I use D again, like I should get just simply D, right? If I assume like both of them are scalar. So if I don't have this is equal to D, something must be wrong. So, okay. So anyway, actually for this guy here, if I if you go through the algebra here, you should get the gradient of T transpose CT with respect to T is equal to C plus C, C plus C transpose uh, T, something like that. So again, like you may want to verify that like, does it kind of like when it degenerate to the scalar case, that is it still correct? So if I degenerate to a scalar case, I will have something like CT squared, right? Like if this is a scalar, this is a scalar, multiplied by C will be simply CT squared, right? So, and if I take derivative of CT squared, in the scalar case will be just 2CT, right? So, okay, and this is good because if I degenerate to scalar case C is equal to C transpose, I'll get back to CT. So, okay. So anyway, so therefore, like take derivative of this is a should be C plus C transpose times T. So okay, I have A transpose A, and the transpose A transpose A is still A transpose A, right? So therefore, I have 2 A transpose A times T, and take derivative of this guy here is equal to, by the way, okay, this guy is actually T transpose uh, A transpose B. Actually, these two are the same. It's T transpose A transpose B. And take derivative of this is actually equal to A transpose B. So it's minus 2A transpose B. So it's equal to 0. So I want to take the derivative and set it to 0. So this is equal to 0. So therefore, like I have T is equal to, so 2 got cancelled here. I can multiply A transpose A inverse on both sides. So I have on here and here. So I will have like T equal to A transpose A inverse times A transpose B. So yes, actually you should see this like many times. Like this is the solution for this guy. And if you have been around for long enough in engineering, like you will definitely see this again and again, like the solution. So that's like something like known as the pseudo inverse. Basically, this part is known as the pseudo inverse. So and so so therefore like we have the something like solution is like this here. T is like the pseudo inverse. We can solve T like this basically. So um and but know that like if this is a solving affine, actually for if I going to solve homography, let's say, remember that for homography we'll have something like that, right? We have basically like we have 9 variables here. I can, of course, this is one here, but I can just make it as a variable as well, just for simplicity in this case. Let's also put it um yeah, actually like yeah, I can put it 1 here. I don't know why it doesn't in this slide here I don't put it as 1 here. So but let's say. So for homography, like I'm trying to do the same thing, but note that like for homography, what happened? Like, uh, yeah, I should modify this slide. This slide is actually not that nice because I don't want to have this as, uh, uh, so okay, well, let's see what I'm going to do. Okay, I guess the easiest thing to do is say, because it's hard to write on PowerPoint. Uh, well, actually, I think I did prepare. Uh, did I? I forgot. Maybe I didn't. Uh, Wait a second. Okay, maybe how about just export as PDF? Oh yeah, I think I did. Let's see. Oh yeah, I did. I forgot. I actually did. Well, why is so big? Let me pull back the chat here. So what I want to say, I don't like this slide a lot. Actually, maybe I can put one here. It doesn't matter. And in general, when I multiply this guy, this will be some value. Let's say xi tutor, yi tutor, and w. Let's say wi, right? Because the last row here is not 001. When I multiply it, it doesn't need to be this, right? But then x pi, the real xi here will be like xi tutor. This one should be equal to xi tutor over wi here, and this one is equal to yi tutor over wi here, and xi tutor is, so therefore is equal to this one, right? So I have xi tutor is like this multiplied by this, right? So I have this one here, and wi here is like this one multiplied by this one here. So I have this guy here. So I have these two. Okay, let's keep this. I guess let's keep this one here. So if I have that, then okay, I have this one, right? Then I can know that again. What are the equation? What are the unknown here? Oh, sorry. What is the unknown? What are the constants here? This xi tutor all are all constants, right? And the unknown here is this h00 up to h22 are the parameters we need to find, right? So then we just rearrange the things like this, multiply on the other side, we get this one here, right? And then now I can move the unknown to all on one side. So I have like h00 up to h22 here. So I will end up something like that, right? For each of the matches here, for all a pair of xi yi match to xi pi yi pi here, I will get two equations like this. But my equations now will be like this one. I mean, like this guy multiplied by this is equal. You see here, although if I have 0 here, previously I have something like this, b is not equal to 0. Now, if I got more matches, I will have something like ah is equal to 0, something like this one here. It's very similar to before. I have like AH equal to B, right? If I try to match with a affine. And in that case, B is not equal to 0. Now the thing now is that I'm trying to again to solve that. I want to minimize H equal to 0. Now, do you see a problem here? What was the solution for H here? If I try to minimize AH equal to 0. Oh, I already show it here. I guess I don't need to add. So, so uh, uh, I can even hide this. Uh, so, but maybe it's a good pause that like just a participation question for you guys, just to see you guys are actually, yes, yeah, um, yeah. The solution is right here, right? So, but yes, it is something trivial. If I just trying to minimize this without putting any constraint, it will be just equal to 0, right? So apparently I can put all 0, then I will get like AH is equal to 0, right? So, but that is not the solution I want because I want to have, remember this H eventually are just uh, the, the coefficient in the matrix here, right? So I don't want to have an all 0 matrix here for my homography. Otherwise, I would basically map anything into the origin. So, so therefore, I want to put in some constraint. I should constrain the, let's say H should have the norm is equal to 1, meaning that like the sum square of all this H coefficient is equal to 1 plus H01 square plus H02 square and so on equal to 1, right? Now, to solve this, then we can write, okay, write, so we have the optimization problem is like this one, right? So again, I will expand this AH, so into something like that, where it will be H multiplied by some matrix multiplied by H is a quadratic form that is subject to some constraint H is equal to some value here. Now the solution, if you think of like, let's say if X up to Xn are the eigenvectors of A transpose A here, and eigenvalues are lambda 1 up to lambda m. Let's say that they're sorted like lambda 1 up to lambda m. Note that like, I can do that. I guess in one of the class we mentioned that like when this is symmetric, then I will have a complete set of eigenvectors and they are all orthogonal. So I have like x1, x2, they are all the inner product like xi, xj is equal to 0. And I can normalize them as well. Xi is equal to 1 themselves. Now then because this is a complete set of eigenvector, I can make them as a basis. So then I can think of like any H can be represented as like the linear combination of this x1 up to xn here. And then so then now if I kind of like expand, kind of like put substitute this H back into the equation. So I have like I want to find let's say what's that? Oh, that's missing here. Yeah, AH here. Oh, okay, yeah, this is fine. This is fine. This is correct. So then if I have okay H is equal to this guy here. So I have the constraint that the norm of H is equal to 1, right? So then I substitute, let me compute the norm of H. So then I just add norm of H is equal to H transpose times H. Then it's substitute this, then expand that. Note that because Xi and Xj are all orthogonal, so I will have all the ij is not equal, it's just a delta function here, right? So I will get the sum instead, it will be like sum ij have a delta ij here. So therefore, one of the sum will be gone because of the delta function. So I will just sum one of them. I will sum over ai square. So therefore, like if I want to make sure the norm is equal to 1, I need to force the argument, force the sum of this ai's here, ai square here is to be equal to 1. And I can do the same thing for the objective function right here, the H transpose A, H transpose A, H. So if I kind of compute that, know that like, because x are the eigenvectors of A transpose A, right? So therefore A transpose A multiplied by x. So basically I have A transpose A here. Originally I multiply by this matrix here. This A transpose A can get inside into the summation. So if I have A transpose A multiplied by xj here, that would be equal to the lambda j xj here. And that is very similar to before, and I ended up something like this. Now this guy will be, I will, what's the value for minimizing this guy? So I will end up something like this. Actually, I asked this question in my other class as well. So if you are in the other class, if you remember like several classes before, like maybe you are able to answer. So I mean, like, okay, let me summarize what we did. So we have represent like H as the linear combination of the eigenvector of A transpose A. And if we substitute this H into like the norm of H and also the objective function here, we'll end up the objective function that we try to minimize is equal to sum of lambda I multiplied by AI squared. And the constraint will end up like this. Sum over AI squared is equal to 1. Now my question is now, what should be my AI if I want to minimize this one here? So meaning that if I want to minimize this, what should be my AI here? I have like A1, A2, A3 up to AN, right? So what should be the value of this A1 up to AN here? Assuming that like lambda 1 shorter, lambda 1 is less than equal to lambda 2, less than up to lambda n. So I guess this most like the final question is like, so there's some algebra here, but as I said, like the final thing is like, if I can represent H as a linear combination of the eigenvectors of A transpose A and substitute into the constraint, then I will need to force the sum of this square of A is equal to 1. And then like for the objective function, I'm trying to minimize, I will get something like sum over lambda I AI square. And now the AI are the things I can vary. Right? I want to kind of find the AI such that this thing will be minimized, basically. This thing will be minimized, but also subject to this constraint here. Yes, very close, but see the, oh yeah, you are right actually. Yes. So uh so okay, I guess I for the West probably not following or somehow. Uh uh so but let's see again. So if I have lambda 1 is less than lambda to lambda n and so on, right? So then like I can just, what's the minimum value I can do? Make sure, note that like I can only allocate this A in a way that uh they cannot, I mean they cannot be all 1. For example, like if I have one of them is 1, then the rest has to be 0, right? Because sum of square is equal to 1, right? So, and for any other, for example, like let's say if I put like 0 here, I put 1 here, what I get here, I will get like lambda 2, right? So let's say if I have like 0, 1, or 0, I will have lambda 2. But lambda 2 will be bigger than lambda 1, right? Or if I have like 0, 0, 1 here, I will have lambda 3, but lambda 3 is bigger than lambda 2 or lambda 1, right? So the best thing I can do would be simply assign A1 to be 1, and then the rest will be all 0, right? So in that case would be uh, basically the value I will get will be just lambda 1, right? So then the minimum value will be just lambda 1. And my best h therefore, my best h? My best h therefore will be just 1. It's actually just equal to x1, right? And x1 is actually the eigenvectors of A transpose A with the minimum eigenvalue. So uh, so that's basically the solution. Oh, and by the way, this is the solution needed for your homework. So therefore, make sure you may not need to understand the derivation here, but you should know the solution. The solution, therefore, is the eigenvector of A transpose A with the minimum eigenvalue. So that will be your H. So everyone get that? That will be needed for your homework actually. So that's why I spend time on this. So you have the A. Let's see if I. Okay, I want to. Okay, so maybe I just quickly go through this RANSAC thing. Uh, so again, because this is extra credit, you may not do that. Like so, the RANSAC idea is very simple. So basically, like you think of like if I use all this to do a match, let's say it's just a linear match here, because I earlier you see like when we do matches, like there's some of these I have outliers, right? So if I try to just like fit in this case, let's say I fit a curve here. If I use all this rest of these like outliers here, I may not have an accurate match. So what I can do is like maybe I can just use some of the candidate and create a match. Let's say this is a match, and the parameters that I find that's the H, and then I try to like go through all the rest of the candidates and see like if they fit well with this H here. If they fit well, then of course you won't have all of them fit well. Then you count like how many of them like fit well, how many of them does not fit well. So then if the one that then you just repeat it multiple times. So then the best H will be the one that like uh, you have multiple that have like most number of time that you fit well. So let me just go to a illustration. I guess it will make it easy to understand. So let's say I have an actual match here, right? So I have like let's say all of these are matches, and and if and these are all matches here. So let's say I have all of these matches. I just pick one of them. Let's say this one, and I'm trying to find the H. Trying to find. Of course, I for the homography I need to have more than one H one match here, right? But here, let's say I just restrict to a translation, so therefore I only need one. So, but in your case, like if homography, you take multiple of them. Then after this, I compute the H here, and then I will just use the look at the rest, like how many of them match well with this H here. So let's say I have like this four of them matches well, and then this two does not match well, right? So okay, I would say like okay, I have two of them, or like I have four of them like doing well. So now, then I pick a next candidate, let's say this one, and then again I try to look for all of them like whether they match well. In this case, I only have one of them match well. So therefore, like the first one will be a better candidate of H than the second one, right? So then you just repeat it many times, then that will be your basically. So okay, I'm a bit over time, but I guess what I want to do is just quickly show you the homework. So therefore, like because I for the next 2 weeks, I hope you guys don't mind me to just take a minute something over time because uh then for your presentation, I mostly like will use up the entire class, so I may not have time to talk about the homework. So So just a quick minute, like to wrap up, like for the homework, like it's exactly doing like what we talked about today. So we I have created a Git repository like somehow, and then like you can yeah, you can download the code like here. So you can either download zip or like you can Git clone. So so basically uh I have two images here, and also like I have the Jupyter notebook that I just created. So now I already like reading like some images, like these are the two images I have here. So I pre-computed the warping function already, like sorry, the homography here already. So in the first part, I want you to do is like trying to stitch the images given the homography. You have the non-homography, you are going to stitch them together. So I given you the H here. So and now I show you like this warping function. Let's say I have this H. If I warp this image, I start with this image one, warp with this H here. And for the warping function, you need to give the image size here. Let's say I just got randomly put like 3000, 2000. Then you see like it crop off a little bit because like that warping function, like if if we have a negative translation, part of the image is outside the region here. So by default, when I say like 3000, 2000, it just basically it warp the image and only display, I mean, or like only include the image from like zero to like 3000, 2000, something like that. So then like I also have the another image two that is like basically log warping it. So you see like I have like compute this H. You see like if I warp this image one by H, it will align well with the image two, right? So if I okay, the first part, as I said, like I want you to stitch them together to create a function like this. So you have like input image one, input image two, you have like two homography that you're supposed to input. Like uh, in this example here, H1 will be just equal to my given H here. H2 will be just an identity. And then like I'm also you input the frame size there, like the output size here. So in this case can be 3000 and 2000. So if you implement the whole thing, like you have something like that, like as I said, like H1 is H, H2 is identity. You put them together, implement the stitch function. If I show that, it should be something like this. So here it's not apparent because you see like I have part of that is go outside the is crop, right? So but you can kind of see that it's actually stitching together. So there's a transition here. It's not very clear, but so there's an extra credit, like 5 point extra credit. So to find the output to find the automatically find the output size of the image, and also like if you need to shift the image, I find the translation that's needed. So because as you see, like for this given H here, the image actually get out of bound, right? So what we want is actually we want to get a translation to translate back the image, like uh, to get what I mean is like originally the origin is here, right? So origin is here. So I want to basically translate the image like by this much. So then like I will have like this part here like get back to uh inside. I mean like within bound. So more precisely, if you implement the function correctly, so you will get back a translation matrix and also the appropriate size for the stitch image. So then like you can input to your original function there. So you should translate your original input homography by T, and also like with the calculated image size, then you will get something like that. So this is the first part. And the second part is I want to exactly solve like this, uh, 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 trying to find the homography. So earlier we said that like to what we want to do is wait a sec. Yeah. in question 1, we give you the homography, right? In question 2 here, what I prepare here is I have already uh, wrote the code here to find the descriptors and also the key point, and then also create a matrix already. If you want here, you should be able to generate the matrix. The matrix are available here, and then what you want to implement is find the homography. That's the part where we say we're going to find the minimum eigenvectors of A transpose A. And also like that's an extra credit to just do the RANSAC. Okay, I'm totally out of time. So, but do you guys have any questions or something? Yeah, 2 and 4 are extra credit, right? Like if you want to go beyond that, yeah. Oh no, yeah, there's 2 and 4 meaning homography here is not extra credit, but this part is extra credit. As I implementing the RANSAC is extra credit. Here to automatically find the size of the output image from the translation is extra credit. Yes. And yeah, you have 3 weeks to work on that. So, but I'm just thinking because for the next 2 weeks we will be mostly doing presentation and don't have time to pause to talk about this. So, but if you guys have any questions, just Discord me. So, okay. If there are no more questions, I guess I will just stop here. So, we'll have kind of like presentations next week then. So, I'll see you guys then. Yeah. Okay. Thanks.
Professor,
Yes.
I have a question
Yes.
about the code in the this GitHub. I just downloaded and
Yes.
tried to run this code.
Yes.
Oh, I see. I see. I
Yeah,
have.
yeah. You cannot just run it
Oh, I
literally
see.
because you need to fill in
I
some
see.
function. Yes.
Because I just run it and I
Yeah.
got
Yeah. Yeah.
an error message.
Oh yes, yes, yes. Actually, like that's a good point. Like, but yeah, you need to yeah fill in the
Yeah,
functions.
yeah, I see. And also, I have a question in the lecture.
Yes.
One thing is when we find the minimum of the H, I mean, we need to find the solution H.
Yes.
Why we have to constraint the norm of H1?
It doesn't necessary to be one. It can be something else. But uh, you need to constrain it to something, maybe some constant. Because as we mentioned, right, if you don't put in the constraint, then a trivial solution will be just H equal to 0, right? And that is the best solution. Definitely is the best solution, but you don't want that solution.
Mhm.
So
So,
therefore, you just constrain that norm to be some non-zero number. So for
mhm.
simplicity, you can just like constrain it to be 1. Yeah.
Yeah, I understand.
Yeah.
But what I'm concerned about is when you find the solution of H, which is not unitary, then maybe this affine matrix cannot just transform one image to other and then cannot get it back to the original one.
It won't. It won't get back to the original one. It's not. H. Okay. If you think of H here, H does not need to be unitary. Here, yeah, definitely it is actually definitely it's not because when H is the if H is a transform matrix. Okay, let me get to the first line maybe. I don't know. Home. Yeah, I guess this is a good slide.
Yes.
Yeah, actually, the only unitary matrix is the rotation, right? The transport is equal to I mean you do the minus theta is go back to itself. Actually, for all the matrices, it's not unitary. So
Oh,
you
I
think
see.
yeah yes
So, oh yeah, but so when you take the inverse, so for example, let's take an example for a scale.
yeah that's inverse, but know that like
It's
when
just
you have when you, the condition for unitary is like uh you have like let's say like orthogonal, like U transpose U transpose U is equal to identity, right? So it means
Right.
that the inverse is actually equal to U transpose.
Yes.
So for scaling, it's already not like that, right? If you have the inverse, it's 1/2, 1/2, 1 way.
Uh-huh.
Yeah, so
Right.
it's not equal to the transpose. Yeah.
But what I concern is, so when I take U inverse times U must be 1, right?
Yes, yes. Yes, you can, okay, what you mean is like it doesn't,
So even though it's a scale function, when you take the inverse, so it
yeah.
is 1 over Sx, 1 over Sy, yeah, 1 over 2, 1 over 3,
Yeah.
1. So that is fine, because when you multiply the 2, 2, 1 times 1 over 2, 1 over 2, 1 is 1, identity matrix, right?
Yes, okay. I guess you get a little bit confused about unitary orthogonal. So the unitary condition is like this. You need to have an orthogonal will be like transpose like for real matrices.
Mhm.
Um, so when you say unitary orthogonal, it means something like this. So uh, uh, so for scale, I guess you think about invertible matrices. You're thinking like whether
Maybe,
like
yeah, maybe,
they are
yeah.
invertible or not. So
Mhm.
yes, there's no promise that it's invertible basically.
Uh-huh.
So you generate the H, it doesn't necessary to be invertible. I'm actually, if you don't have the constraint, definitely it won't be invertible because like H is all zero matrix. There's no way it will be invertible. You have like just all zero. It will just always like converge to the origin. Then no way is to be invertible.
Mhm.
But in general, solving that thing, like it won't promise you to get an invertible matrix. Yeah. So, but yeah.
Okay, so actually what I thought that, so what I initial question was, when we look at the H is a general or affine matrix, like
Yes.
defined by H 0, 1, 0, 0, 0, 1, something like that. So you said we have 9 unknowns.
Oh yes, yes, yes. You can. Yes, actually, yes, you are right. I hear. I'm. Uh, that's you're right. I mean here, like because I for the when you're using homogeneous coordinate,
Mhm.
scaling does not affect your uh it's basic scaling is meaningless, right?
Uh-huh.
I multiply by c here, it won't change the transform itself
Right.
because yeah scaling does not mean anything. So I can scale anything. I can put this one here. Yeah, I can actually put one here,
Mhm.
but this is actually more preferable in
Mhm.
terms of estimation because like if I put one here, like I kind of like pre-constrain in the sense like how the coefficient are going to be behave.
Mhm.
Um, it's hard to explain. I guess I'm not actually very good in like numerical analysis, but this is kind of related to some kind of numerical analysis that like if I constrain this to be one that like it will um it it won't give me like as most of the time it won't give me like as robust solution than if I allow this to be like arbitrary value first.
Uh-huh. I
Yeah,
see.
yeah. So
So you're saying it doesn't necessarily to be the norm of H is 1, right? You cannot have, we can
oh,
have
the
any
solution will be
value.
one because I after the constraint I will normalize to one. But what I'm saying that like solving that with for say the norm is equal to one, right? Okay, let me elaborate to
Mhm.
make sure like I'm clear myself. So that's two way to solve this. So if I allow this to be like arbitrary, all line values to be like arbitrary, then solving that like eventually will be solving the minimize the norm. Okay, I have like uh, A transpose A H. So minimizing that subject to like norm is equal to one, let's say, right? So and and another way like will be I just force this to be one. Okay, I force this to be one to start with. Then I will end it up with something similar to before we'll have like ax equal to b, something like this. Because like if I force this equal to 1, then I have, okay, let's say I have 1 here, I have 1 here, and let's say go to the next line. I guess I have 1 here, I have 1 here, and this is like some kind of constant, right? So xi h3 minus 1 is some constant, and this one actually I can pull on the other side here.
I see.
I have 1 variables left. Basically, it was similar. It would be before like I have like a transpose x equal to b, solve that kind of stuff.
I
So,
see.
but the solution for this guy is actually not as stable, as robust as the solution for this one. Therefore, yeah, I kind of like go for this one. Like, yeah, but
Okay,
the,
yeah, some makes sense.
yeah,
Okay, I got it.
yeah. So okay. So I missed something like for you guys. Like if you're still here, uh, but unfortunately I don't have enough time. Like I'm really running out of time. When you guys trying to solve this, you don't want to do A transpose A. Actually, you can, depends on how many matches. Actually, in this case, maybe you can. But it's the same. Finding eigenvector of this is trying to find the single vector of this thing, like just A itself. If you know this single value decomposition, um, and so you can solve the single value, try to decompose A with the single value decomposition and look for the one with the smaller single value. I forgot like which one I implement. Maybe it's okay because the dimension is not big here. Yeah, probably you can get away with that. I don't know. But if your A has a huge dimension, meaning that you have, let's see. Yeah. If A is has a huge dimension, then probably it's not a good idea. But it's okay. Yeah, it's okay. So I think for the homework, you probably just get away just solving like A transpose A. Yeah. So okay, that's it. I guess unless you have more questions and so on. So I'll see you guys next week then. Yeah.
Okay, thank you.
Thank you.